So, welcome all to this 26th St. Luke's Memorial Lecture, and we are very fortunate to have Professor Deepak Dhar among us to give this memorial lecture. To start with, I request our Dean Academic Professor Amita Lahiri to present a flower bouquet to the speaker. Please. And I also request Professor Lahiri to kindly give the big overview of this memorial lecture.
Thank you, Rajit. Good afternoon and welcome to the 26th St. Luke's Memorial Lecture. This is our premier named lecture. We hold 4 named lectures. This is the one that has been running the longest. There is also one named lecture after Professor C.K. Majumdar, one named after Subramaniam Chandrasekhar, and one named after G.N. Ramachandran. The St. Luke's Memorial Lecture has been running since 1988. The center was established in 1986. In 1988, the speaker was Leon Van Hoff, who had been the Director General of CERN. And since then, many famous scientists have given the St. Luke's Memorial Lecture, including Dean Stanley, Chris Llewellyn-Smith, E.C.G. Sudarshan, Virendra Singh, Fujikawa, Sam Edwards, Sienna Rao, Jayant Narlikar, Martin Bloom, S.R.S. Varadhan, Abhay Astekar, Rashid Sunayev, Ashok Sen. Professor Olugen Ketarli gave the St. Luke's Memorial Lecture twice. He gave the lectures, both lectures after he got the Nobel Prize. And 2 years ago, it was Anton Zeilinger who gave the St. Luke's Memorial Lecture, and he got the Nobel Prize this year. So this year we are glad to have Professor Deepak Dhar with us to deliver the St. Luke's Memorial Lecture after getting the BOSE Memorial Lecture. And to introduce him, I request our director, Professor Tanushree.
Good afternoon, ladies and gentlemen. It's our absolute honor and privilege to have a very distinguished speaker, Professor Deepak Dhar, today to give a very distinguished memorial lecture, as has been already mentioned. That's the most distinguished lecture of our institute, namely the St. Luke's Memorial Lecture. As you have already read, whatever brief biodata you have, by this time you know that he has received the Boltzmann Prize, which is given by the International Union of Pure and Applied Physics, and that is given every 3 years. And he is the first ever Indian to be honored with such a kind of very distinct accomplishment. So as an Indian, we are all very proud about it. So thank you once again for accepting our invitation. And he received this Boltzmann Prize in the year 2022. And this year he has been awarded as Padma Vibhushan, which is another very distinct award in this country. And as I understand, he is a small award, which tells that if you have the ambition and the drive, you can really, really go to the top. So he comes from a small place in UP and studied in Allahabad University, his bachelor. And after that, his master was from IIT Kanpur, and then straight to California Institute of Technology, earning his PhD. And after that, he came back to TIFR. He had his probably the longest career there, spent time. And I can see many of his collaborators, friends from the TIFR days, the audience. And he has possibly got almost all kinds of coveted recognition one can dream of. Sitting in India, he got the Shanti Sharup Bhatnagar Prize. He is the fellow of all three Indian science academies. He is the fellow of the World Academy of Science, as well as he got the TOAS Prize. And his field of research is that of the statistical physics and also stochastic processes. First time I met him, that was a stat physics conference, as I remember, where Stanley was also there, and there were very interesting discussions on the sand pile. I still remember that. And he has been known for his work on various different domains, in fact, phase transition and statistical mechanics in the problem of course, the sand pile, looking at the self-criticality of the sand pile, looking at the fractals, defining the renormalization group for the fractals, and then even working in the domain of the evolutionary theory. I didn't know about it. And then also with the spin glass and magnetic system, the slow relaxation in the magnetic system, just to name a few. Then he has been known for his work on phase transition with the hard sphere. And from hard sphere, he has gone to hard rods, which will be the topic of lecture today, as I understand. So we are eagerly looking forward to this lecture. And thank you once again, and a warm welcome to SNBOSE Science. Thank you.
Let me start by saying that I'm very thankful to SNBOSE Center for this great honor of asking me to give SNBOSE Memorial Lecture. SNBOSE is, of course, one of the heroes of Indian physics, and in particular, a hero for me as well. So I'm very happy to pay some kind of tribute to him when I see that I made a mistake with the first slide itself. Apologize. Maybe you will see some other typos along the way, and you will excuse me for any inadvertent and carelessness which may follow after this. So in this talk, I will try to discuss some work on phase transition in hard rods on the D-dimensional lattice. The problem is quite straightforward, easy to define for students. I think high school students can understand the problem as statement of the problem, and that makes it an interesting problem. There has been a lot of work from starting with Own Sagar around 1950, and the progress in this problem has been slow. And so we are very happy to have made some small additional contribution in that, which I will tell you about. So let me continue. Okay, so this one is done with a student, Agam Shah, who was a student at IISER Pune, now abroad. This is a 50th thesis project, and with R. Rajesh, who is at Science. And there are some published papers, and so you can look them up. I'll see further details later. Okay, so this is the general plan of talk. I understand that this is slightly general audience, so I will introduce the notion of geometrical phase transitions, and then go on to discuss phase transition in hard rods, which is the particular problem I will try to address. I will discuss the low density disordered filament. So this problem undergoes two phase transitions. First, I will discuss the first one, which is somewhat better understood. And then there is a sort of semi-detour to the problem of packing of hard rod, full lattice. You take a 2D square lattice and pack it fully with rods. And how many ways can you do this? But this result for the entropy of packing of hard rod is needed for the next part, which is the second phase transition in this problem, which I will discuss, and then I will summarize. Okay, some parts of the discussion are a little bit technical, by that it meant algebraic, but I think I will try to ensure that the main ideas are not lost in algebraic details. Okay, so just back up a little bit, and one of the things which have been people have been studying for a long time in statistical physics in the last 50-70 years has been phase transitions. And the interest in understanding phase transitions, of course, started from the fact that there are these spectacular phase transitions of ice changing to water and water changing to steam, which all of us have seen in our childhood. And we like to understand them from a theoretical point of view. Can physics explain why ice melts to water and water melts to steam? So, of course, now we understand it at some level, and this is because the interactions between the molecules are like that. And so then there is the standard statistical mechanical postulate of equilibrium statistical mechanics, which says that if you give me the Hamiltonian, and then I can say that different configurations occur with probability given by exponential minus beta h. And then you just have to calculate averages over different possible configurations. And the problem of phase transitions reduces to the problem of calculating averages given the probability distributions. Okay? So what is the interaction which gives rise to all this behavior? Now, water is a complicated molecule, but you can take something else, take alcohol or benzene, but they all undergo these kinds of phase transitions from solid to liquid to gas. And a fair model, not perfect, of these interactions is that the molecules have Lennard-Jones type interaction. If you bring them close, they are repelling, and if they are kind of far away, they are attracting. So in Feynman's lectures in physics, volume 1, in the first lecture, he says that if the whole physics was lost and you had to only preserve one sentence, that sentence would be that the molecules interact repulsively at short distances and attractively at large distances. So that's what we understand, and we believe that if we take this kind of interaction, then from statistical physics you can get these phase transitions from solid to liquid to gas. So this is the Lennard-Jones interaction. It says pairwise here, because of course it's not fully right. There are three-body interactions and more complicated stuff. And the water molecule is asymmetric, and there are angle-dependent interactions, kinds of complications. But we can take a simplification that you take pairwise additive interactions of the Lennard-Jones type, with only distance-dependent interactions, and then what happens? So it turns out that with Lennard-Jones interaction, you cannot actually calculate the partition function exactly. And so to understand them, we would like to use some easier to handle interactions which show similar behavior. So I said the Lennard-Jones interaction is already a simplification, but we need to simplify the problem even further to make theoretical progress, to make our understanding better. So in this lecture, I will focus on what is geometrical phase transition. Geometrical phase transition is a simplification of the original problem, because what it does is that it takes only the repulsive part of the interaction between molecules and forgets the attractive part. And even the repulsive part for us will be either infinite or zero. So, either they overlap or molecules don't overlap. If they don't overlap, they have no interaction. This is not realistic, but it turns out that lots of predictions of this simpler model are still interesting. They show phase transitions, and we would like to understand them better. So it says the study of geometrical phase transitions, because now there are hardcore interactions, so it becomes a problem in geometry. And so it's conceptually simpler, and we don't need to know what is energy and what is temperature. So you just have some objects which are, say, some rods which you can put on a two-dimensional space, lattice or continuum, and only some configurations are allowed and not allowed, and that's all there is to it. There is no need to introduce the word temperature. So it is certainly simpler in this sense. The phase transitions are only functions of the density of these objects, what fraction area is covered. And so we need to work only with notions of fluidity and geometry, and no temperature. Okay. So this problem of hardcore particles and hard rods has a long history, starting with the work of Onsager 1949. So Onsager's work we discuss it a little bit more, but it is supposed to be the first work on geometrical phase transitions. But that was an interesting question for me, because people have discussed phase transition in hard spheres. And that problem was studied in 1930, which is much before Onsager's work. And it undergoes a phase transition, and that's a geometrical phase transition. So why is that work not considered as the first work on geometrical phase transitions? So it turns out that people at that time were discussing hard spheres, and they were discussing corrections to the ideal gas laws, to the interaction, that is virial series kind of stuff, but they knew the virial series is the finite radius of convergence. What happens when the virial series breaks down? They knew it breaks down someplace. And of course, all kinds of approximations were used, but they were uncontrolled approximations, and it wasn't very clear what happened. But I found a paper by Kadku where he speculates that what happens in hard spheres at higher density is that it becomes a crystal, which is true. But it was, I guess it was a guess, not a speculation really, but there was no real proof there. And that is why Onsager is said to be, his work is said to be the first work on phase transitions in hardcore systems or geometrical phase transition. But I would like to say that maybe, but the phase transition hard spheres is older and perhaps is better deserving of the word first study of phase transition. But another model which is also very interesting, which is around 1960 page also, is called the percolation model, which is also easy to define, and a lot of people have studied a lot, which I will not discuss here now. It's just the reference is made for the sake of students. You can look it up and see other examples of geometrical phase transitions. Okay, so we are studying hard particles, so you can study other shapes. So we will study hard rods, but we take triangles, squares, etc. So we put them in a box and maybe shake a box a little bit and see what happens. That's the problem. Okay, so turns out that the structure of what you get depends a lot on the shape of the object, and different shapes give different answers. And a simpler problem at some level, it was studied a lot by mathematicians at one stage, including Kepler. What is the densest working you can get given a particular shape? Okay. But if the shape is different, let us say tetrahedron, regular tetrahedron, how do you, what the best backing you can get with regular tetrahedron? That's a slightly more complicated geometrical problem, which maybe some of you have an answer for, but you can take other shapes and you can ask how can you pack them efficiently. And it's an interesting question. So we will, might look at that. But We will take further simplification of this problem. We will study the problem on a lattice. Why do we do this? That is just because I find easier to work on that. Somebody else can do something else. But for me, because it seems natural to simplify the problem where you work, the centers of multiply only on a grid, not in 20 mode, and the problem becomes easier to work with because you can count the number of configurations instead of doing integrals, you are counting. Okay. So here is some pictures. So this is a three-dimensional space, and the objects are some. The first one is a square of size 2 by 2. This is a grid actually, which is not being shown. And as you see, if you increase the density, this is some typical configuration of these kinds of stuff. And you can see there is some change in the structure when you change the density. And while visually you can see this, can you actually quantify this in some way? Or is there some phase transition which is happening in this picture when you go from left to right? It's a kind of question you can ask. And what is this phase transition and how do you understand it? How do you quantify it? Can you calculate where it occurs? And those are the kinds of questions you can ask. The next shape is long rods. So these are length 4 and width 1. And you can see again that as you increase the density, something happens. I don't know. And when you go from left to right, that is just increasing density, and these are some of the kinds of configurations you can generate. Okay. Is there something you can say about the picture on the right or picture on the left? How do you characterize a random configuration of these objects? That's the problem we will address. But some more pictures. So these are Z-shaped objects, and the lower one is called L-shaped objects. The lower one is called T-shaped objects. And these things are called tetraminos. And because they are made of 4 cells, and these pictures are taken by some other people of guns. And so I'm just saying, maybe I should see the upper picture first. So it is 2009. So what I'm trying to say here is that lots of these problems have been studied, and they are interesting, and they give rise to very cute pictures. So that is the reason for studying the problem. Okay. It's too far. Sure, I beg your pardon. That's so far. Okay, so this is done. Okay. Now, so of course, in this lecture, I will study a theoretical problem, which defines something. But the model of hard rods with no other interaction is actually a pretty good model of tobacco mosaic virus in water. Because tobacco mosaic virus looks like a long rod, cylindrical, and all the virus particles have roughly the same length. And so, they in water, they take various orientation. But if the density of these particles is high enough, then they become parallel to each other, which is intuitively rather simple. If you take needles and try to fill the needles in a box, then at low density, the needles can be put in whatever position. At high density, to try to put a lot of needles in a box, then they all become parallel to each other. That was the observation of Gonzaga. And this is an experimental realization where you see that when the things become parallel, the solution becomes optically active. And you can shine light, and it rotates the plane of polarization. Then you do polarizer, analyzer, then you see different colors. Okay. So this is a macroscopic system which you can see the phase transition in a hard rod system. And this experiment is easy. You can do this in some undergraduate level. So now coming to theory. So I will discuss the Onsager model was actually a long rods in solution, but the rods lie in a continuum. He did some calculation. This calculation was done in some slightly artificial limit of rods whose diameter goes to 0 and length goes to infinity, such that the total volume remains constant. It's a little bit an artificial, but for this particular limit, he could obtain some exact results. And but it's actually hard to make progress with the Onsager's work. And so Swansea introduced this model on a lattice. So he said that maybe the problem becomes easier to handle if you work on a lattice. The lattice model is slightly different from the continuum model, because in the continuum model there is a degree of freedom which is the orientation of rods. And on the lattice it becomes discrete, so there are only two orientations allowed. And the continuous degree of freedom which gives you rise to some contribution to entropy, which is important, is totally missing. So this model is slightly different from the other one, but it undergoes the same phase transition. At low density, there is a phase in which rods are in arbitrary orientation. At high density, there is a phase in which they are kind of parallel, I suppose. That's what was guessed. And so this was the question that, okay, suppose I change. Onsager's result is kind of understood and seems reasonable. But suppose I change the model to rods on a lattice. Is there a phase transition still? So this problem, this Swansea's work is 63. There was a review article on the subject written by Deepak and Prof in 75. And they said that this is not very clear that there is a phase transition in this problem on the lattice. So even around 1975, it was not clear that there is a phase transition in this model. Why? The point is that it is known that for k equal to 2, which is the dimer problem, there was a proof that there is no phase transition to a phase in which nematic order, rods become parallel. And that was all there is known. Then there was some Monte Carlo evidence from us and from other people, which showed that for 3 and 4 also there is no phase transition. So then there is a question, is there a phase transition at all? It was not clear that a phase transition occurs. And so the reason for the doubt, for the confusion, was mainly this, that if you take these rods on a lattice, then there are many configurations in which you can pack the thing in. So, we are saying that if you increase the density, then there is a phase transition to ordered case. Now, I make the density 1, which is the maximum possible density. What happens there? It seems rather clear that at density 1, there is no order. Because there are many configurations, one of them is shown below. And these configurations, most of them are random. They are equally likely to horizontal or vertical. The configurations where everything is parallel, where everything is perpendicular, are 2 out of so many. So they don't contribute. So it is clear that at density 1, there is no order. So you are increasing density at density 1, there is no order, then maybe there is no order at all, ever. That is what one might guess. And the total number of configurations one can get is exponential in the volume of the system. The proof is given here. It is a very short proof. So you take a very big square and break it up into small k by k squares. Each rod is of length k. And each square can be covered in 2 different ways, as shown here, either horizontal or vertical. And the total number, since each square can be covered independently, total number of ways is bigger than equal to 2 by n by k squared. So it's an exponential in n, where n is the number of sides in the system. Okay. So that is a proof that there is no orientation order at density. So then becomes the it's what is done with Anand Mohan Ghosh, who is in the audience, but virtually. In 2006, we studied this problem using Monte Carlo simulations. And we showed by Monte Carlo that actually there are two phase transitions in the system. At low density, when you increase the density, the system becomes ordered. At some intermediate density like 0.89, and almost everything is ordered. But then you increase the density further, there is a second phase transition where the thing becomes disordered again. This is the high density case. And so this is the Monte Carlo evidence in favor of two phase transitions in the system. And the phase transitions are only governed by increasing density. Okay, so now we would like to understand both. Instead of one phase transition, we have to understand two. And so, first phase transition from the low density to the disordered nematic phase is quite well understood. At intermediate density, the ordered state is higher entropy than the disordered state. For the students, in the beginning, this sounds like contradictory. You know, I always thought that disordered state is a higher entropy than the ordered state. Why are you telling me the opposite? Okay, so the answer is that if you make the needles parallel to each other or nearly parallel, then they lose in the orientational entropy. But they can move around more freely, so they gain in translational entropy. The entropy has two factors. One is due to the fact that you can place the things in various places. The second, you can orient them in different ways. So you lose a little bit in orientational entropy, but you gain much more in translational entropy. And so the system prefers to go into the ordered case. So in the square lattice, there are two ordered states. You know, that things can be horizontal or vertical. And in the general theory of phase transitions, this says that maybe I don't want to work out too much detail. Then it looks like Ising model that there is a disordered phase and there is an ordered phase. You say there are two possible ordered states, and so the phase transition is in the Ising universality class. And the argument given here is a little bit hand-waving, but actually that is under coarse graining. The details of the interaction get lost, and only the fact that there are two phases which compete with each other survive. And then this is the expectation based on some general ideas of universality and renormalization, and they are satisfied by Monte Carlo simulations. So we would kind of say that we understand this phase transition. So now I come to this problem of entropy of long rods at Deepak. So I already argued that the number of ways you can take these rods and take a big lattice and cover it fully is exponential in the area of the big system. And we can define entropy per site at full packing as S of K, which is the log of the number of ways you can do this divided by the area of the system. I take K by KL by KL. That is the reason I take it KL by KL is because unless K is a multiple of L, maybe there is not even a one configuration if you pack everything. Right? If I take a 39 by 39 of lattice and try to pack it with 6 muds, because 39 times 39 is not a multiple of 6, you won't be able to do it, whatever you do. That's a very robust argument which says that, you know, the number of ways is exponential, but it might be 0 if you are unlucky or if you are not careful. So we will be careful. We will work with lattices which are multiples of whose length is multiple of K. Then the number is exponential, and that is the definition of S of K. So the exact value of this S of K is known only for K equal to 2. K equal to 3, 4, 5, the answer is not remains hard problem. The K equal to 2 problem is called the diamond model, and it is one of those very classical problems in statistics where you learn how to solve this problem. That is one of the things every statistical physicist is expected to learn. Okay. So, but here we will show that in the limit of large K, again the problem becomes a bit simpler. So this large K limit is when things are long roads. So it's the same approximation which Onsager had invoked to get his result. We will invoke the same kind of limit, but the approximation is different. But the idea that long roads make life easier, and we are using Onsager's experience. And so we will show that S of K goes like A log K by K square. That, we will do. But interestingly, we find that A is actually equal to 1. So quite often people are able to get, asymptotic results about this thing behave like this. But the coefficients of the, whatever exponent dependence one has are harder to determine. And here you will find an even more interesting result that you can take this problem in deep dimensions, 3, 4, 5. In each case, A is 1. Okay, so that is a slightly surprising result at first. You would say, well, okay, in 2D it goes like log K by K squared. What happens? It goes like log K by K squared. What is the coefficient? It's still 1. Okay, so that also it's not very hard, as you will see, understand it, but that was the issue. Okay, so this is the technical part. So we have shown that S of K goes by log 2 is bigger than equal to log 2 by K squared, that was a bound using K by K decomposition. But you can do better than this. And better than this is shown in the picture below. So you take K by very long strip and you cover it with vertical or horizontal rods. This can be done in more ways. Last time we were saying K by K squared. Now there are no K by K squared. Some vertical rods are only 3 at a time. Right? So, of course, all the, if you want to cover 6 by 6, here it is bigger. If you want to cover by K, you can do it still, but there are more ways of covering it. But can I calculate how many ways I can cover a strip like this with fully with rods? The answer is this problem is not very hard because there is a recursion relation. Suppose omega r is the number of ways of covering r by K rectangle. Then you just look at the first column. You can either put a vertical rod there or not put a vertical rod. If you put a vertical rod, the rest of the space can be filled. It's r minus 1 in length. You have to fill it. So the omega r is equal to omega r minus 1 plus. The other way is you have to put everything horizontally in the first K things. And then you have to fill with r minus K the rest. So this recursion equation is fairly straightforward to write. Once you have the recursion equation, then you can just it is known for linear recursion equation that then the solution is lambda for r for large r, where lambda is the root of the equation. And this is a simple algebraic equation, so you can show that. So here say that maybe should this. For large K, lambda is near 1, so you write lambda is 1 plus b by K. So, but K is large, so we are taking lambda to the power K, K may be 99, It's a polynomial equation, but it's a high order polynomial. So can we, what happens is the solution there? So it says lambda you write as 1 plus b by K. Lambda to the power K becomes exponential K. That is some exercise in algebra which I think most of you can do. And so we get the equation determining d exponential t. This equation is also a little bit tricky, but it's known in mathematics. Okay. So the solution leading order is log K, but then there is a correction which is log K, and there is a next correction which is log K. There is a next correction which is log K. It keeps on going like this. You will not be able to go to the next or power law term beyond this log K. So that is the reason for interest in this problem. Then you have to study the solution of this equation or asymptotics of this equation in some other way. And so with that one can do. But anyway, for us the life is very simple. We just say that V goes by log k leading order, and then Sk by this is an lower bound on the actual lambda, and so this equation follows. Sk goes like log k by k squared, or it's bigger than equal to log k by k squared, the coefficient 1. Okay, so now you need an upper bound on this number as well. And we are lucky that the upper bound also goes by log k by k squared with coefficient 1. And so we are sure of this result. This upper bound is due to the Gunashvili and KZ. And it's reported in this paper. But the argument is very brief. And these were the Russians they wrote in their style, which was very brief. And only the experts can understand what is being said. And all the details of the argument were not given. But anyway, they give enough details so you can construct some part of the argument. And the argument is like this. You will not follow the product, but at least you will get the spirit of the argument. Yeah. So what he said was that let us take the big lattice and let us consider the k, break it into k squared sublattices and consider some of these one sublattice with spacing k, the purple squares. First, I will cover these purple squares. So each purple square can be covered in 2k ways. You can put in k ways horizontally and k ways vertically. So I put place each of them in ways, and I will tell you which way I have covered it. I have covered it with the leftmost or second leftmost horizontally, or I covered it vertically. So give a specification of the covering of each of these purple squares. But now I have to fill the full lattice. So each of these sides can be covered in at most k ways. And so this said omega, so they proved that if you give an assignment the superlattice size, you give the spacing of each purple side has to be covered like this. Can I complete the covering? So the statement is if you try to complete the covering, it can be done in at most one way. Sometimes you cannot do it. It's not possible. If it is possible, there's only one way to do it. That's not easy to prove. But it's a clear statement of what is intended to be. And you don't need to know anything other than basic geometry. And so you can prove it yourself. That is the challenge for this. Prove this statement yourself that there is at most one way you can complete the covering. But once you accept this statement, then this gives the bound. And then take the log of this divided by L squared, it gives the log 2k by k squared. We showed it's bigger than log k by k squared, less than log k by k squared. As far as log k is concerned, it is fixed and the bounds are tight, and so you get the equal. Okay. The generalization to higher dimension. That 8.1 also holds in all higher dimensions. And this is because suppose I work in z equal to 3 and I want to cover a three-dimensional space with these rods like this. So one efficient way of doing this is to break the space into layers, to cover each layer by rods, and then each layer you can cover in many ways, and so that 3D space can be covered in many ways. Okay. There are also other ways of covering in which some rods are vertical. But let us say, so this is clearly ways of covering for 3D lattice is bigger than ways of covering of 2D lattice per side. Okay. And now what I can do is I can develop a perturbation theory in the density of vertical rods. And this result says that S k d equal to 3 minus S of k d equal to 2 This order k to the power minus k. This is the order of term which comes up with perturbation theory. The first order perturbation will be like this, second order perturbation will be square of this and so on and so forth. I cannot calculate the coefficient very well. Maybe I calculate the first term. But this is a series in k to the power minus k. If the series is convergent, then this is the answer we get. So this is not a proof, but this is it's only say order. I'm not saying much more. So presumably rigorous proof is not there, but there is a perturbation theoretic proof order by order. Okay. So leading behavior, is unaffected. For large scale, these two don't differ much. We were only saying log k by k squared. So that is not going to be affected by this, and it's the same. And you want to go to d equal to 4, you use the same argument again, and so. So you get the same result is true in arbitrary dimensions. And when I saw this first, I thought that was quite amazing and surprising, and worth telling you about. Okay. So this just actually develops the proof which I gave in words before with a little bit more detail, so that you can understand that it is not just words, there is some calculation is involved. So we used the method introduced by Bellman and Niggams in 1967. And so what they said was, you want to study how to cover this, but let us introduce two kinds of rods. Horizontal rods have different activities than vertical rods. And then we will do the problem if they are not equal, and then consider the case when they are equal as a special case of this. But the case when one of the activities is 0 is easy, because if every rod is horizontal, then you are covering space by horizontal rods. Here, we are not considering, sorry, so this is full packing. So we are doing this 3D problem. No? So the 2D problem has a lot of entropy, then there was another layer. Then I developed a perturbation in Z prime, order by order, and then tried to sum up the series with perturbation. So very interestingly, so omega Z Z prime, if there is omega Z0, then the rest vector you expand in powers of Z prime. My k is 100. So there is no term to order Z prime. There is no order term to order Z prime squared. The lowest order term which shows up is Z prime to the power k. That is because in each layer, I started with some lattice. If I just put one vertical rod, then you cannot fill it. The rest of the horizontal layer cannot be filled completely by other rods, because it doesn't multiply. It has to be covered by k rods. If one hole is there, you cannot cover it. It's a very standard argument, repeated many times, even for dimers. Okay? So the lowest order term is Z prime over Z to the power k. Next order term is Z prime over Z to the power k. And so, this one already seems to make me feel that, oh, I don't have to worry about this. This series is not important. But anyway, you can actually. So there is a finite contribution to the second part, but it is exponentially small in k for a fixed value of Z prime. But unfortunately, in the end, I will put Z prime equal to Z. So I have to be careful in my estimates. And we will not do this here. I'm giving you an indication of the, that you have to discuss how these terms converge, not converge, what they behave like. Those are slightly technical details I will skip. But in the end, the answer seems to be that term by term they behave well, but you cannot actually show that the answer is well behaved, even if the prime equal to Z, because it's a perturbation series. And at Z prime equal to Z, all ordered terms may be equally contributing. But anyway, so since the work is a bit technical and I don't want it to get lost, I will give you the final answer of what we are going to show. And then we go ahead and give you some details. So in the end, we will show that non-rigorous argument that the nematic to high density disordered phase transition is actually a first order transition. And it is a first order transition in all dimensions. And this is some, we will discuss this picture again, but there is a chemical potential here, and this is the density of holes. When you decrease the chemical potential, the density of holes goes up. So these are the different graphs. But for large K, beyond 6, they seem to develop a kink. So that is the first order transition. This is a numerical result. These are not exact calculations, and they are based on some strip. But so we will. So there is some numerical evidence that this is actually a first order transition. And now we will give you some theory behind it based on perturbation theory. But there is more. So, there is a first order and phase transition. But what happens at the first order phase transition? The density of vacancies jumps from a value epsilon 1 to a value epsilon 2. And it occurs at a particular value of the chemical potential. So we will like to know at what epsilon 1, what epsilon 2 does it occur for a fixed K. And this is the results. Epsilon 1 goes like K by K squared, and this ratio tends to 1.
This is for all dimensions, including B equal to 1?
No, all dimensions bigger than 2. 1 is considered as a sphere case. No. So you are right. For all D bigger than 1, it should have been said. Okay. And we can also tell what is the chemical potential, mu star in K and B. And it also has this limit, much more messier. But I think what it says is that mu star goes like K of K. Because if mu star goes like K of K, mu star by K will be exponential of K, there is a K, then we cancel with K. And I don't worry about higher terms just now. So mu star goes like K of K, and again the coefficient of that has to be 1. And then you can look at what is the second density of holes at the other end of the first order transition, epsilon 2. And it says that it goes to 0 exponentially fast in K. And so if you multiply by any K to the power n for any positive value of n, you take a large K limit. Since this is going down exponentially, this will matter, and it will give some details. So, now these results are again valid for all K, independent of dimension, and there are no pre-multiplicative constants in the leading K. And that result is interesting, it unexpected in the first. Eventually, perhaps if you think very hard, it becomes reasonable and expected, but that is an afterthought. Okay. So, to hurry up a little bit. So, let S of epsilon be the entropy per side. When the vacancy is epsilon, then of course you can take all the rods to be horizontal in one direction. It's a bound on the entropy. S is bigger than this nematic, which is a fully nematic state. And this we can calculate, this is one-dimensional problem, so it has an explicit expression for epsilon. And S of epsilon differs from this, but only comes to order epsilon to the power K, which we are K is very large, so we are saying it's very small. For any finite K, doesn't really matter. So I can forget about it and take this to be the exact entropy for expression for entropy. It is not exact, but it is good enough for my purpose. So we can determine the partition function per side. So now I can do the same kind of calculation which I did before for fully packed case. But now it turns out that when you calculate this omega of the triangle is the activity of the block. Now there can be a contribution to first order, because now there are vacancies. This argument used the fact that if you put only vertical rods, you cannot complete the covering. So you can calculate this coefficient A1 and it goes like epsilon to the power k. But k is large, epsilon is small, so it's still working for me, even though, there is a first order term, but it is exponential in k. And so, we would like to go home. But it turns out that if you take the epsilon tending to 0 limit, then z goes like epsilon to the power minus k that cancels with this. And the contribution of the first order term in the end is finite and not zero. So things are a little bit more subtle, but cannot just hope for the best. But it worked out. And this calculation I will skip. And so this is the variation of the relative contribution of the correction to the input as a function of epsilon. So it turns out that there is a minimum. And if you put epsilon equal to 0, then the correction becomes epsilon equal to 0 is on the left. This thing is a slow slope. But eventually it keeps on going and the correction will be. But at any finite value of epsilon, this is 10 to the power minus 25, 10 to the power minus 10, is a change in entropy. So I am allowed to take the k goes to infinity limit in this stable way, and it will work. Okay, I'm not going to take the epsilon goes to 0 limit first, so that won't work. But so this is a slightly untypical perturbation series. Doesn't work at epsilon equal to 0. It's guaranteed not to work at epsilon equal to 0. But for finite epsilon, it works very well for large k. Okay, so now let's come back. So we have a formula for this estimatic, which is this curve. And estimatic has the property that as epsilon goes to 0, that formula gives you 0. But I know that at 0 and full vacuum problem had a finite entropy. So actually the S0 is not 0, but it is non-zero. And how do I reconcile these two things? Reconcile by the famous tangent construction, Maxwell tangent construction. So the true curve must be such that it coincides with this curve here. But at some point, if you go here, then it gives you some answer and there must be a tangent construction. Okay. So the answer jumps from here to here at a particular value of z, which is given by the slope of this curve. And so there must be a first order transition. So since the actual function has to be convex, and this function is convex here, but it has to be coming here, meet at 0, which we calculated. So the only way for this to work is that this region has to be thrown out, and it has to be replaced by the tangent construction. Now, once I agree to the tangent construction, I can, I know the value of h0. I can find out, and I know the equation of this curve. I can find out where the tangent will meet the curve, and that gives me the value of epsilon 1, and the slope gives me the value of mu, which is the chemical potential, and epsilon 2 in our approximation is 0.
But this line is still approximate or exact?
This one is asymptotically exact. For large k, it becomes more and more. For any k, it is incorrect, but it is incorrect only to exponentially small terms. Okay, so this is, I think, the point. In the region 0 to less than epsilon 1, it is better entropically for the system to separate into parts. One part is nematic order with hole density epsilon 1, and one part is no holes. Because the part with no holes will still have finite entropy if you use that. And then in other part you have finite vacancy, so you can generate a lot of waste in the ground. And so there is a phase separation, which is the first order transition. Okay, so now where I told you that you can actually calculate the place where the intercept occurs, and this is where you get these results. So now we like to argue that these asymptotic results remain unchanged even if you work with the true function s and not s nematic. And I will not go through this part. It's just that the correct difference between them is exponentially small in k. So it doesn't matter. We will not this. But we can take order by order that this works. And then you can increase the, we did some, the estimate of this, the 1 digit calculation. You can make improved calculations, which are still exact, which give bounds, which are consistent. So, you can take configurations like this into account, some finite number of them, and they still give you the same answer. They don't change the qualitative behavior of the answer. And so this is the summary. The hard rods undergo two-phase transitions as a function of density of activity of rods. For large K, the entropy of K at full cracking is log K by K squared into 1. The subleading terms in K. For all hypercubical lattices, with B bigger than 2. And asymptotically exact result for the position of the first order transition and the density jump across the first order transition. And so it says here, given the simplicity and robustness of these results, one would hope that, a nicer and more non-perturbative argument can be found to these results. That unfortunately we have not managed. Okay. But I do believe that if the result is simple enough, then a simple proof would perhaps exist. And, so we are still for a cleaner proof of this, which is less dependent on these technical details of sleep extractions. Okay, so let me stop here.
It's very interesting talk. So before I start the question and answer session, I request our director, Professor Sharma, please present the
It's mandatory.
yes, mandatory. So you can take some questions.
No, so, sorry, what is the statement? So, K large, but for finite K, there is a transition?
Yeah. For people, I showed you some picture, but that's not a proof. But the expectation. Even for K equal to 10, there is a first order. For all K bigger than 6, there is a first order.
No, but still there is no proof.
There is no proof.
So the other thing, you talked about some bacteria, right? Yeah, tobacco something. So that bacteria. So I think, there the dynamics is important, right? Here, you are considering all configurations, but dynamically they cannot be accessible. For example, density 1.
Yeah,
you cannot change things.
No, so the question whether if you take virus, then can be treated adequately in the equilibrium ensemble of the just hardcore interactions. I think that's correct. But adequately is the word, because of course, actually, if you take two virus particles very close to each other, they have extra interaction. But in order to explain the phase transition in the virus system, it's not necessary to include that interaction in our discussion. And one should simplify without using detail.
No, my question was different. So I'm saying, so in increasing the number of bacteria, number of the dimers, bacteria dimers. So now you start with some configurations, but that may not reach the equilibrium state at all, dynamically. So then you actually do not see any transition.
No, so of course you can prepare systems with very long rows which are not equilibrium ensembles. This question here being addressed in the equilibrium ensemble. If the ensemble is not equilibrium, additional complications will arise. but we are not addressing that here.
Okay. Yeah.
Yeah, so very informative talk. So I had two questions. One was you said that this model where you had two transitions. This belongs to the IISER University class.
First transition.
First transition belongs, not the second one. So the second question is that if you start playing with the the types of rod you have, here you had only one type of rod. If you had like two different scales of rod, will the university class change?
So of course in some other systems, this is called poly dispersed rods. So what one guesses that if you have poly dispersity in the length of rods, then the nematic case is more favored. The stability of the nematic case is enhanced by the poly dispersity. Whether the hard, in our argument, the fact that the fully packed case has a finite entropy was very important. So if that poly dispersity is of the type such that even that point is lost, then you can say that second transition occurs just at the end and its width is width of the high density phase is 0. But that will occur only for particular types of poly dispersity. In other cases, the basic argument that there will be a first order transition is expected to continue.
And maybe one more question if you allow. So the rods can be thought of as ellipsoid objects, right? So which are convex shapes. If you work with non-convex shapes, for example, these kind of physics still manifest?
No. So in the first I showed you that all kinds of funny things can happen if you take other shapes.
Okay.
So no, you can have much more complex behavior. If the shapes of rods, you can make S-shaped objects. They will be very much more complicated. Many more is it of exotic type can be found in funny shapes.
Any more questions?
If you the same thing happens also in continuum system. Like how does this 7 compares in the continuous system? How do you fix the number 7 in continuums?
How do you fix that?
Number 7.
What
is k equal to 7 means in continuum?
I really don't know. That's what we find numerically. It has a kind of hand-waving explanation. It says that the place where the transition occurs seems to go like A by K. And numerically in the data, A turns out to be around 6. So, if K is less than 6, then the transition will occur with this extrapolation formula that density bigger than 1, which is not possible. So, that's how the 6 comes. But that's just a numerical, fact.
No, but in a continuum system, will it still happen? Do you expect a transition in a continuum system? Like the rods are finite length, but they can really orient and rotate.
So, no, I don't understand this much better. So, why 6, why not? Why 5 doesn't give a phase transition? I wouldn't. Because we are dealing here with the large scale limit. With the large scale limit, I was very lucky that it was working until 6. Should it work at 5 as well? No luck.
No questions? Right.
I allow more orientations. So does it change the phase transition that is showing in the system?
Actually, one can go through this part of the argument. The first transition depends on the number of states allowed. So it becomes 2 equal to 3 Potts model universality class instead of 2 equal to Potts model universality class designing models. But it remains in that time. The second one also remains, the argument goes through, it remains first order.
So in a work construct, you showed that when we come from 3 dimension to 2 dimension, the perturbation creates which is a function of k to the power minus k something. How can you prove this?
These results are perturbation theory results. So order by order. Yeah, so this order by order, each term you can calculate the first order correction, second order correction, each of them satisfy this.
From students, any more questions from students? Someone online has any question? If not, then we conclude the session and we can thank Professor Dhar for the very excellent talk.
Okay.